The universe was supposed to grow slowly, like a baby learning to walk. But some of its very first galaxies skipped the crawling stage entirely. The James Webb Space Telescope found galaxies born only a few 100 million years after the Big Bang, already carrying black holes 100 million times heavier than our Sun, and star clusters worth 100 billion suns. Scientists call them universe breakers. Today, we travel to a galaxy caught eating its neighbor before Earth existed, a giant galaxy that refuses to spin, and hundreds of strange red dots that might be baby black holes wrapped in fire. If your mind wants answers as much as ours does, tap subscribe and stay close, because some of these mysteries just got solved, and the truth is stranger than the mystery itself. Prepare yourselves. We begin at the edge of time. A newborn should not be able to walk out of the delivery room and order a coffee, yet that is close to what astronomers found when they pointed a new telescope at the darkest, oldest light in the sky. The universe is about 13,800,000,000 years old. For most of the history of astronomy, scientists pictured the earliest galaxies as small, messy, and thin, like a toddler still learning to stand. Little clumps of gas, a few scattered stars, nothing grand. That picture held for decades, because no instrument could see far enough back to check it. Then, the James Webb Space Telescope opened its golden eye in space, and the toddler picture broke apart in a matter of weeks. Astronomers found galaxies that existed only a few 100 million years after the Big Bang, and these galaxies were not small or messy at all. They looked packed, heavy, and strangely organized. Some already glowed with the light of tens of billions of stars. A few looked less like a baby and more like a fully built city, complete with lit streets and skyscrapers, sitting where a single tent should have been. Imagine finding a fully grown oak tree in a forest that was planted last week. That is the size of the puzzle scientists are facing. Under the standard model of how the universe grew, gravity needed time to gather gas into clumps, clumps into stars, and stars into galaxies. Lots of time. Millions of years for the first stars to ignite, millions more for those stars to die and seed the next generation. Millions more again for galaxies to merge and grow heavy. Every step in that chain takes patience, because gravity is a slow and gentle force, not a rushed one. So when the very first snapshots of the infant universe showed galaxies already massive, already structured, and already aging, the timeline buckled under the weight of it. Scientists checked their instruments. They checked their math. They checked the light itself, stretched and reddened by the expansion of space, to make sure they were really looking as far back in time as they thought. The results held. These galaxies were exactly where the models said they should be too young to exist in that shape. Some researchers now describe a handful of these objects as almost impossible, given everything we thought we understood about how galaxies are built. Others suspect the mistake is not in the universe, but in our assumptions about it. Maybe the earliest stars formed faster than we expect. Maybe galaxies merged sooner and more violently. Maybe something about the infant cosmos worked differently than the cosmos we see today. Whatever the answer turns out to be, one fact is now hard to avoid. The first billion years of the universe were not calm and empty. They were loud, fast, and strange enough to make a grown galaxy from what should have been barely a spark. Picture the whole history of the universe squeezed into one calendar year. On that calendar, the Big Bang happens at the first tick of January. Earth does not form until September. These overgrown ancient galaxies would have to build their entire mass in the first few days of January before anyone had figured out how to light a match. And the deeper astronomers dig into these ancient snapshots, the stranger the story gets, starting with just how many stars some of these newborns already carry. 100 billion suns. That is not a typo, and it is not an exaggeration. It is the estimated weight, in stars alone, packed inside some of these ancient galaxies, measured in the mass of our own sun as the counting stick. Say that number slowly, and it still does not sound real. 100 billion. each one a burning furnace, roughly the size of our own star, all born and shining inside a single galaxy. Our Sun already outweighs Earth by more than 300,000 times. Now, imagine 100 billion suns, all fused into stars, all crammed together in a single galaxy that finished building itself before the universe turned 1 billion years old. To put that in a size we can actually hold in our heads, our own Milky Way took more than 10 billion years to gather its stars into the shape we see tonight. These ancient galaxies did something close to that same job in roughly 1/10 of the time. It is the difference between building a city over a full career and building it before finishing high school. So how do astronomers even weigh a galaxy that sits 13 billion light years away, far too distant to visit or touch? They read its light. Every star gives off a certain color and brightness based on its size, its age, and its temperature. Small, cool stars glow a dim red. Hot, young stars blaze blue and white. By splitting a galaxy's light into a rainbow, a method called a spectrum, scientists can count roughly how many stars of each type must be shining to produce that pattern. It works a little like judging how many people are in a stadium by listening to the size and pitch of the crowd noise, without ever seeing a single seat. That method works well for nearby galaxies, where the light arrives strong and clear. It gets much harder for galaxies sitting near the edge of the observable universe, where their light has been stretched, dimmed, and faded across billions of years of travel. Even so, when scientists ran the numbers on a handful of the earliest, brightest galaxies Webb had found, the totals kept landing in the same shocking place: tens of billions of stars, sometimes more than 100 billion, built while the universe was still, cosmically speaking, in diapers. A mass that large changes the whole conversation. A small, early galaxy with a few million stars is surprising, but forgivable. Models can stretch to fit it. A galaxy with 100 billion solar masses of stars, fully formed within the first few 100 million years, is a different kind of problem. It challenges the entire chain of events that is supposed to lead from a smooth, nearly featureless early universe to galaxies at all. And here is the detail that keeps astronomers awake at night. These mass estimates might actually be too small. The method of reading starlight, useful as it is, has a well-known weakness. It is very good at counting bright, hot, easy-to-see stars, and much worse at counting the small, dim, quiet ones hiding in the background glow. If a galaxy's population leans heavily toward those faint stars, the true weight of that galaxy could be hiding in plain sight, uncounted, unseen, and waiting for a sharper set of eyes to finally catch it. Every telescope is a time machine, whether it looks like one or not. No rocket boosters, no spinning dials, just glass and metal quietly gathering light that is older than almost anything you will ever touch. Light does not arrive the instant it leaves a star. It travels, and travel takes time, even at the fastest speed the universe allows. When you look at our sun, you are seeing sunlight that left its surface about 8 minutes ago. Look at a star further out, and you might be seeing light that left before your grandparents were born. Look far enough, and the light reaching your eyes left its source before Earth even existed. That is the trick behind finding the earliest galaxies. Astronomers are not looking for old objects. They are looking for old light. The farther away something sits, the longer its light has been traveling to reach us, and the further back in time we are actually seeing it. A galaxy 13 billion light-years away is not a picture of it today. It is a fossil, a frozen snapshot of what that patch of space looked like 13 billion years ago, mailed across the universe, like a postcard that took 13 billion years to arrive. For decades, that kind of postcard was almost impossible to read because of a problem built into the fabric of space itself. The universe is expanding, and has been since the Big Bang. As light crosses that stretching space on its long journey, the light itself gets stretched too. Its wavelength grows longer, and its color shifts away from blue and toward red, a phenomenon called redshift. Push that shift far enough, and visible light stretches clear out of what human eyes, or ordinary telescopes, can even detect. It slides into infrared, invisible to us, felt only as heat. That is exactly the kind of light the James Webb Space Telescope was built to catch. Instead of a mirror tuned mainly for visible light, like older telescopes, Webb carries a giant golden mirror more than 21 feet across, built from 18 hexagon-shaped segments that folded up like a piece of origami to fit inside its rocket, then unfurled once it reached space. That mirror is tuned to gather faint infrared light, the exact kind that ancient, red-shifted starlight has become by the time it reaches us. Catching that whisper of a signal takes more than a big mirror. Heat from the sun, Earth, or even the telescope's own machinery would drown out the faint infrared glow it is hunting for. So Webb flies nearly 1 million miles from Earth, far past the moon, shielded behind a sunshade the size of a tennis court, cooled down to nearly 400 degrees below zero. Only in that deep cold and deep dark can its instruments pick out the dim red whisper of a galaxy that shone its light before Earth's oceans had formed. The result is a telescope that sees earlier, peering closer to the very beginning of time than any instrument built before it, gathering starlight that everything before it was simply too blind to catch. And the moment scientists pointed that golden mirror toward the darkest patches of sky, one of the very first things staring back at them was something nobody expected to find so soon after the beginning. A galaxy already carrying a black hole heavy enough to swallow entire star systems whole. Black holes are supposed to be patient monsters. They do not appear fully grown. They start small, usually born from the collapse of a single dying star, then spend millions or billions of years slowly feeding on gas, dust, and the occasional unlucky star that drifts too close. Each meal adds a little more mass. Growth by growth, bite by bite, a small stellar remnant can eventually swell into a supermassive black hole, the kind found anchoring the center of large galaxies like our own. There is a speed limit built into that process, and it is not optional. When a black hole feeds, the material falling in heats up and glows so fiercely that it pushes back against anything else trying to fall in behind it, a bit like a narrow doorway that gets more crowded and harder to squeeze through the faster people try to rush in. Physicists call this the Eddington limit. Cross it too far, and the black hole starts blasting away the very fuel it needs to grow. It is nature's built-in brake pedal, and it caps just how fast any black hole is allowed to gain weight, no matter how hungry it is. Under that limit, growing a supermassive black hole from a single dead star up to millions or hundreds of millions of times the mass of our sun should take a very long stretch of cosmic time. Astronomers had a rough budget in mind for how long that budget should be, built on decades of watching black holes grow in galaxies much closer to home. Then Webb looked back toward the first billion years of cosmic history and found black holes that had blown straight through that budget. Some of these ancient black holes already weighed in at tens of millions, even close to 100 million times the mass of our sun, sitting inside galaxies that existed when the universe itself was less than 1/10 of its current age. Running the numbers backward, there simply was not enough time, under the normal feeding limit, for a black hole born from an ordinary dying star to reach that size that quickly. It would be like expecting a lemonade stand to become a global company by the end of its first afternoon in business. Scientists are left staring at two uncomfortable possibilities, and neither one is small. The first is that something about black hole growth in the early universe worked differently than it does today, perhaps feeding faster, or starting from a bigger seed than a single collapsing star. The second is that our picture of these black holes, built entirely from reading their light across billions of years of stretched, faded distance, might be catching them at a strange and misleading moment, making them look far larger or far younger than they really are. Either answer forces a rewrite of some part of the story, and this same uncomfortable choice between a universe that behaves differently than expected and a measurement that is quietly fooling us keeps showing up again and again as scientists dig deeper into these ancient galaxies. It shows up first, and perhaps most surprisingly, in the simple act of trying to weigh a galaxy's stars, where an entire hidden population may have been sitting in the shadows the whole time, uncounted. Try counting fireflies next to a bonfire. The bonfire is so bright that it drowns out most of the small, flickering lights around it. You might catch the shape of the fire perfectly, yet still walk away with no real idea how many fireflies were actually out there in the dark, quietly blinking just beyond the glow. Now imagine trying to do that same count from 13 billion light-years away, through a haze of stretched, faded light, with no way to walk closer and check by hand. That problem, oddly enough, sits at the center of one of the biggest questions in early galaxy research. When astronomers measure how much a galaxy weighs, they are not putting it on a scale. They are reading its light, and light has a serious bias built into it. A single giant, blazing hot star can outshine thousands of smaller, cooler stars combined, the same way one bonfire can outshine an entire field of fireflies. That means the light streaming out of a distant galaxy is dominated by its brightest, most massive stars, even if those stars make up only a small slice of its true population. Smaller stars, the dim, slow-burning ones that make up most of the stars in any galaxy we can study up close, contribute only a faint whisper to the total light. In a nearby galaxy, astronomers have other tools to catch that whisper, patient tricks built from decades of close, detailed study. In a galaxy sitting 13 billion light-years away, with its light stretched, faded, and squeezed through a redshift that pushes it deep into the infrared, that whisper becomes almost impossible to separate from the noise. For years, most mass estimates for these ancient galaxies quietly assumed that the mix of small and large stars looked roughly the same as it does in galaxies closer to home, simply because there was no better assumption available. It is a reasonable starting guess. It is also, potentially, a very costly one. If the earliest galaxies in the universe built stars in a different ratio than modern galaxies do, favoring either far more small stars or far more giant ones, then every mass estimate built on the modern ratio could be quietly wrong in one direction or the other. It cuts to the heart of the entire mystery. Every headline about an impossibly massive early galaxy depends on that mass being measured correctly in the first place. If the bonfire method is hiding an entire unseen population of fireflies, then some of these already startling galaxies could turn out to be even heavier than first reported, deepening the puzzle instead of solving it. That is exactly the question a team of astronomers set out to answer by pointing Webb's sharpest instruments not at galaxies still bursting with young stars, but at a stranger, quieter target: 9 ancient galaxies that had already stopped forming stars altogether, gone dark and still, while the rest of the infant universe blazed around them, offering a rare, clean chance to finally separate the bonfire from the fireflies hiding in its glow. No young, blazing stars left to drown out the signal. Just the cooled, settled light of a population that finished growing long ago, waiting to be read correctly for the first time. Some galaxies never stop building. Fresh gas keeps falling in, fresh stars keep igniting, generation after generation for billions of years. Other galaxies burn hot and fast, use up their fuel early, and then quietly retire. Astronomers call those retired galaxies quiescent, a word that simply means calm, settled, no longer forming new stars. Most quiescent galaxies we know about are old and nearby, the kind of galaxy you would expect to find resting after a long, full life. A team of astronomers went looking for something that should not exist under that description. Retired galaxies, sitting near the very edge of the observable universe, from a time when the cosmos itself was barely out of its own infancy. On paper, a galaxy that old, that far back, made almost no sense to search for at all. They found 9 of them. 9 massive galaxies that had already shut down star formation entirely, discovered at a distance where their light had been traveling for well over 12 billion years. In other words, These galaxies were old by the standards of the universe's own age at the time, already retired while the cosmos itself was still young, meaning they must have raced through an entire lifetime of furious star birth and shutdown in a fraction of the time it usually takes. That alone would be strange enough. But these 9 retired galaxies also handed astronomers a rare gift. Remember the fireflies and the bonfire from before. In a young, star-forming galaxy, blazing hot new stars drown out the faint light of smaller, older ones, making an accurate count almost impossible. In a quiescent galaxy, the bonfire has already burned out. There are no fresh, blazing young stars left to hide behind. What remains is the settled, mature light of a population that finished forming long ago, a much cleaner signal to read. Using Webb spectrograph, an instrument that splits a galaxy's light into a detailed rainbow of information, the team studied these 9 ancient, quiet galaxies more closely than anyone had managed before. They combined that data with earlier ground-based observations, sharpening the picture even further. The goal was simple to state and painfully hard to achieve. Look past the obvious, dominant light and try to detect the subtle fingerprint left behind by the faint, small stars normally lost in the glare. It is a bit like trying to hear a single quiet voice inside a packed stadium, using only a recording of the total crowd noise. One astronomer on the team described it plainly. Measurements like this were simply impossible until very recently. It took a telescope powerful enough to magnify extremely distant galaxies, spectra of exceptional quality, and brand new analysis techniques, all working together just to catch the faint signature of small stars hiding inside these cosmic giants. What that careful, patient search actually turned up did not calm the mystery of the early universe. It deepened it. Buried in the fine details of that starlight was evidence of a hidden population, stars too faint to have ever been properly counted before, waiting silently in the data until someone finally knew how to look for them. What the team found waiting there would push these already enormous galaxies even further past what anyone had thought possible, and by a shockingly large margin. The hidden fireflies were real, and there were a lot more of them than anyone expected. What started as a careful technical check on old data turned into one of the more unsettling results in recent memory. When the team finally teased apart the faint signal buried inside those 9 ancient, retired galaxies, they found a population of small, dim stars far more crowded than the standard assumption predicted. A real, substantial jump rather than a rounding error. In some cases, the true stellar mass of these galaxies came out 3 to 4 times higher than earlier estimates had claimed. Sit with that number for a second. A galaxy that scientists already considered impossibly massive for its age turned out to be carrying far more mass than any small undercount could explain. It may have been carrying up to 4 times more starlight worth of mass than anyone had given it credit for. One galaxy in the study, already flagged as an extreme case before this new analysis, came out potentially 4 times heavier once the hidden faint stars were finally counted properly. That kind of jump rewrites the puzzle's difficulty level entirely. Think back to the oak tree planted last week. Scientists had already been struggling to explain how a full-grown oak tree could exist in a forest that young. This new finding is the equivalent of walking back out to that same tree and discovering it is actually 4 oak trees, grown together, tangled into what looked from a distance like a single trunk. The mystery did not shrink. It multiplied. There is a strange silver lining tucked inside this discovery, and it has nothing to do with galaxies at all. If the earliest galaxies really did build far more small, cool stars than large hot ones, that has consequences for something much closer to home: planets. Small, cool stars are exactly the kind of star that tends to host small, rocky worlds in comfortable, long-lived orbits, the type of environment where life has the best odds of getting a foothold. If that pattern held true across the early universe, then rocky planets circling quiet, low-mass stars may have been far more common in the first billion years of cosmic history than anyone previously guessed. For the astronomers running the numbers, though, the immediate takeaway was less about planets and more about a warning. Every model built to explain how galaxies form now has to explain both how galaxies grew so big, so fast, and why they built such a lopsided mix of small stars and large ones while doing it. That detail cannot simply be assumed away anymore. It has to be built into the model from the ground up, or the model will keep getting the wrong answer. Which raises an uncomfortable question that reaches far beyond these 9 retired galaxies. If the earliest stars really formed in a different ratio than the stars filling galaxies today, what would cause that shift? The answer takes us straight into the strange chemistry of the infant universe, and a question that sounds almost too simple to matter. Were the ingredients for making a star even the same back then as they are now? Or was the early universe baking its stars from an entirely different recipe? Picture a giant bag of mixed candy, the kind you buy for a party. It sounds like a strange place to start a conversation about the early universe, yet it turns out to be exactly the right one. Every bag follows a rough pattern. A handful of big chocolate bars sit near the top, easy to spot, easy to grab first. Underneath them sits a much larger pile of small, plain pieces, the ones nobody reaches for right away, but which actually make up most of the bag's total weight once you tip it out and count everything. Star formation follows a strikingly similar pattern, one astronomers describe using a formal term called the initial mass function. Whenever a giant cloud of gas collapses and breaks apart into a fresh batch of stars, it does not produce stars of all one size. It produces a mix, and that mix is lopsided in a predictable way. A small number of large, hot, blazing stars form alongside a much larger number of small, cool, dim ones. In nearly every star-forming region, scientists have studied up close, in our own galaxy and its close neighbors, that ratio holds remarkably steady. Astronomers often call it the Standard, or Milky Way, mix. For years, when scientists tried to estimate the total mass of a distant galaxy from its light alone, they leaned on that same steady ratio as their default assumption. It made sense to do so. It was the only ratio anyone had ever measured directly, since it is the only one close enough to study star by star. Apply that same candy bag pattern to a galaxy's light, and you can work backward from the visible chocolate bars to estimate how many small, hidden pieces must be sitting underneath. But what if the earliest galaxies in the universe filled their bag differently? That is the exact possibility the hidden star discovery raised. If the earliest generations of stars formed with proportionally even more small, dim stars than the standard mix predicts, a pattern scientists now call a bottom-heavy population, then every mass estimate built on the standard candy bag ratio would be systematically too low. The method itself would still be sound. It would simply be running on the wrong recipe. It is a genuinely open, actively argued question. Some conditions in the infant universe could plausibly tilt the recipe that way. Gas clouds back then were simpler, built mostly from raw hydrogen and helium, without the heavier elements that later generations of stars would seed into space. Cooler, simpler gas can, under some models, fragment into smaller clumps more easily, favoring the birth of more small stars relative to giant ones. It is a reasonable, testable idea, and it is far from settled science. What it means for the practical business of weighing galaxies, though, is enormous. If the recipe really shifted, then every headline about an impossibly massive early galaxy might be reporting a number that is still too small, not too large. And that single, quiet assumption about candy bag ratios turns out to control something far bigger than bookkeeping. It controls how fast scientists think an entire galaxy is even capable of growing in the first place, and how much of that growth has been sitting there unseen the whole time, hiding inside the numbers. Every galaxy runs on a kind of budget, and every budget has a deadline attached to it, whether anyone can see that deadline or not. It has a certain amount of gas available to burn into stars, and a certain amount of time to burn it in. Spend that gas too slowly, and a galaxy stays small and quiet for a long stretch of cosmic history. Spend it fast and efficiently, and a galaxy can balloon in size far quicker than anyone watching from the outside would expect. The hidden faint stars discovery changed both how heavy these ancient galaxies turned out to be, and how fast scientists now believe they must have been spending their budget. Here is the part that stings. If a galaxy's true stellar mass is 3 or 4 times higher than earlier estimates claimed, that mass did not appear out of nowhere. It had to be built, star by star, out of available gas, within the same tight window of cosmic time that already felt too short to explain the smaller, original estimate. A bigger final answer, squeezed into the same limited amount of time, means an even faster rate of star formation than scientists had already struggled to explain. Picture 2 bakers given the exact same few hours to fill a bakery with bread before the morning rush. One baker was thought to have baked 1,000 loaves in that window, already an impressive pace for a single oven. Then someone actually recounts the shelves and realizes there are 3,000 or 4,000 loaves sitting there, not 1,000. The clock on the wall never changed. Only the workload did. Whatever process filled that bakery had to be running far hotter and far faster than anyone had given it credit for. That is the situation astronomers now face with these early, once quiescent galaxies. They built a shockingly large amount of stellar mass in a short window of cosmic time, likely even more of it than first believed, packed disproportionately into small, faint stars, all before shutting down entirely and going quiet. Something about star formation in the infant universe appears to run on a different gear than the star formation we observe happening in galaxies today. Whether that difference comes from denser gas clouds, simpler chemistry, more violent surroundings, or some combination none of it fully understood yet. Every explanation on the table sounds strange. None of them sound impossible. There is one obvious way to build a galaxy's mass quickly, without waiting patiently for slow, steady star birth alone. Do not build it from one clump of gas working alone. Smash 2 galaxies together, and their combined stars, gas, and momentum merge almost overnight in cosmic terms, jumping a galaxy's mass upward in a single dramatic event instead of a slow crawl. That exact scenario has already been caught in the act. Astronomers have actually caught one of these ancient mergers happening in real time. Frozen mid-collision by the light web managed to capture, showing 2 young galaxies fused together into a single object already 10 times heavier than anything else found at its age. It turned a statistical puzzle spread across 9 quiet galaxies into a single, jaw-dropping snapshot of chaos, caught red-handed, mid-collision, 13 billion years ago, 510 million years after the Big Bang. A wrecking ball swung through the darkness, and nobody was there to hear it. There was no sound to hear anyway. Space does not carry noise, but if it did, this particular collision would have been deafening. 2 young galaxies slamming together with enough combined gravity to build something 10 times heavier than any other galaxy known to exist at that same early age. Somewhere in that tangle of light, an entire new class of ancient monster was quietly being born. An international team of astronomers spotted it using the sharp eyes of the James Webb Space Telescope, and what they found was not a single, tidy blob of light, the way most distant galaxies first appear. It was a mess, in the best possible scientific sense. The object showed 2 separate clumps of stars sitting close together, connected by a long, stretched-out tail of material, trailing behind them like a scarf caught in the wind. That shape is the fingerprint of a merger, the visible signature of 2 galaxies caught mid-collision, their stars and gas already tangled together, but not yet fully blended into one smooth shape. Earlier telescopes, including the Hubble Space Telescope, had photographed this same patch of sky before and seen only a single point of light, one dim, unremarkable dot among thousands, easy to overlook in a field crowded with far brighter targets. It took Webb's much sharper vision to finally resolve that single dot into its true chaotic structure. What looked like one small, ordinary object turned out to be two galaxies actively crashing into each other, caught in the exact act of becoming something far bigger than either one started out as. The lead scientist on the discovery described how, at the moment of observation, this merging system already outweighed every other galaxy found that early in cosmic history by roughly a factor of 10, built from a head-on collision happening while the universe itself was barely out of its first half-billion years, a toddler throwing a punch heavy enough to knock down a grown adult. That detail matters far beyond just one impressive object. It offers a working answer to the growth speed problem that keeps surfacing again and again in this story. If a single galaxy has to build its own mass, slowly and patiently, star by star, hitting 100 billion solar masses within the first several 100 million years, looks close to impossible. If two hungry young galaxies simply slam together, combining their stars, their gas, and their momentum in one violent event, that same final mass can be reached almost overnight, in cosmic terms, without breaking a single law of physics along the way. Mergers like this were always expected to happen somewhere in the early universe. What nobody expected was to actually catch one, frozen mid-collision, in this much detail, this early, and this massive. It is one thing to suspect that violent collisions helped build the first giant galaxies. It is another thing entirely to watch two of them locked together, tails flung out behind them, in the act of becoming a monster, close enough to study its wounds while the fight is still happening. Two galaxies do not merge the way two raindrops merge, smoothly and instantly, becoming one shape the moment they touch. A galactic merger is slow, violent, and messy, stretched out over many millions of years. Even though from 13 billion light-years away, it can look, at first glance, like a single peaceful smudge of light. Peaceful is the last word anyone would use if they could actually watch it unfold up close. Here is what is actually happening inside that smudge. As two galaxies drift toward each other, gravity does not wait for their stars to physically collide before it starts wrecking things. Long before any two stars actually crash into one another, and stars almost never do, since even a crowded galaxy is mostly empty space, gravity begins yanking gas, dust, and stars out of their normal orbits. Tidal forces stretch each galaxy into long, curved streamers, the same stretching force that raises tides in Earth's oceans, just scaled up to a galactic size. That is exactly the long tail astronomers spotted trailing behind this ancient merging pair, a scarf of stripped stars and gas flung outward by the sheer violence of the encounter. That violence does something else too. It compresses the gas caught in the middle of the collision, squeezing it tighter than it would ever get squeezed sitting quietly inside a single, undisturbed galaxy. Compressed gas collapses faster, and faster collapsing gas means faster, more intense bursts of new star formation. Mergers combine two galaxies' existing stars, and they often trigger entirely new waves of star birth in the process, adding fresh mass on top of whatever mass the two galaxies already carried into the crash. Our own galaxy is no stranger to this story, just running on a much longer clock. Billions of years from now, the Milky Way is on a slow collision course with its neighbor, the Andromeda Galaxy, a merger that will unfold over roughly the next 4 billion years before the two finally settle into one larger galaxy. What astronomers caught happening 510 million years after the Big Bang is a preview of that same basic process, just running on fast forward in a universe still dense, crowded, and young enough for galaxies to bump into each other far more often than they do today. That crowding turns out to matter enormously. The early universe was a smaller, tighter space than the one we live in now, since everything had not yet spread apart through billions of years of cosmic expansion. Galaxies sat closer together, gravity had more neighbors to pull on, and collisions that take billions of years to unfold today may have played out on a shorter, more frequent schedule back then. If that is true broadly across the infant cosmos, then this single dramatic merger may not be a rare exception at all. It may be an early hint of a common, almost routine growth strategy, one that could help explain an entirely different kind of oddity Webb had already stumbled across nearby. A galaxy just as young, just as massive, and yet strangely, stubbornly still, sitting motionless in a universe where everything around it was supposed to be tumbling, colliding, and spinning wildly out of control. Every galaxy you have ever seen in a photograph is moving, spinning, orbiting, wheeling through space at speeds that would sound impossible if you felt them. Our own Milky Way spins through space like a pinwheel, carrying our entire solar system around its center once every 220 million years or so. A slow, steady, predictable motion that has been true since the galaxy first flattened itself into a disk billions of years ago. That spin marks one of the clearest signs of a mature, settled galaxy. A system where stars and gas have had enough time to fall into smooth, ordered, circular orbits, all traveling the same direction, the same way water settles into a calm, spinning whirlpool once it stops sloshing around. Astronomers expected young galaxies to look like the opposite of that: chaotic, clumpy, full of gas still falling in from random directions, stars forming in scattered, disorganized pockets rather than a single tidy disk. It takes time, gravitational patience, for a young, messy system to settle down into the calm, spinning shape we associate with a mature galaxy like our own. Then Webb spotted something that broke that expectation almost completely. A massive galaxy, sitting so far away that its light has been traveling since the universe was still very young, showed no sign of the smooth, organized rotation astronomers expected to be missing at that age. Using an instrument that splits starlight apart to measure motion, astronomers can tell whether the near side of a galaxy is moving toward us, while the far side moves away, the telltale signature of a spinning disk. In much the same way, a passing ambulance siren shifts pitch as it moves toward you, then away. In this particular galaxy, that telltale shift simply was not there in the way a young, forming disk should show it. Instead, its stars looked more like a loosely packed swarm, moving in scattered directions rather than one shared, disciplined orbit. The kind of motion normally seen only in very large, mature, elliptical galaxies found much closer to home. Galaxies that had billions of extra years to settle into that random, jumbled state after violent histories of their own. That combination should not exist together. A galaxy that young simply has not had the time, under standard models, to either grow that physically large or settle into that kind of aged, disorganized motion. It is the astronomical equivalent of meeting someone who was born last week and already walks, talks, and carries themselves exactly like someone who has lived a full 70 years. Wrinkles, wisdom, and slow, deliberate movements included, standing right next to newborns who are still learning to open their eyes. Researchers studying the object are still working through what could explain it, and the leading ideas point back to the same suspects, showing up again and again throughout this story. An early violent merger that scrambled its orbits before it ever had the chance to settle into a disk, or a birth process that built the galaxy fast and rough from the very beginning. Either way, this quiet, motionless giant stands as a direct challenge to the entire timeline scientists use to judge how old a galaxy behaves, based purely on how it moves. Astronomers have a name for the kind of motion this strange, silent galaxy shows. They call it dispersion supported, a technical phrase for something fairly intuitive once you picture it. Instead of stars traveling together in one shared, orderly path, like cars flowing around a racetrack in the same direction, dispersion-supported systems hold themselves up through the sheer scatter of their motion, stars zipping in many different directions at once. Their combined chaos balancing gravity's pull, the way a swarm of bees holds its shape without any two bees flying the same line. It looks calm from a distance. Up close, it is organized chaos, held together by motion alone. That kind of motion usually shows up in galaxies that have already lived through a rough, eventful history. Big elliptical galaxies nearby, the smooth, football-shaped giants, found anchoring large galaxy clusters, typically earned their scattered orbits through repeated collisions and mergers, stretched out over billions of years, each violent encounter scrambling the neat, spinning paths their stars once followed. Reaching that scrambled, settled state normally takes a very long career of cosmic bruising. This particular galaxy had almost no career at all, cosmically speaking, when Webb caught sight of it. It existed far too early in the universe's timeline to have racked up billions of years of collisions. Yet there it sat, already behaving like a battle-scarred veteran rather than a rookie. Something managed to scramble its orbits, and scramble them early, using a fraction of the time this process is supposed to require anywhere else in the universe. The leading suspects line up with familiar names from earlier in this story. A single, especially violent early merger, more chaotic and disruptive than the more typical, gentler collisions expected at that age, could conceivably do the job in a hurry, tossing stars into scattered orbits almost immediately, rather than over a long, gradual settling period. An unusually turbulent, gas-rich birth environment, common in the crowded, active infant universe, might also produce a galaxy that starts scrambled from day one, never passing through an orderly, spinning disk phase at all. Neither explanation is settled, and researchers studying the object are careful to say so. What is not in dispute is the observation itself, confirmed through repeated, careful measurement of the galaxy's motion rather than a single lucky snapshot. A massive galaxy, sitting deep in the early universe, moves like it has already lived a long, violent life it should not have had time for. Cases like this keep piling up. A galaxy too heavy for its age. A black hole that grew too fast. A merger caught building mass 10 times faster than expected. A giant that moves like an old veteran while the rest of the cosmos is still learning to crawl. Individually, each discovery could be dismissed as an unusual outlier, an oddball exception hiding somewhere in every dataset. Stacked together, one on top of the other across multiple independent teams and telescopes, they start to look like something else entirely. A pattern insistent enough that some scientists have begun asking a far bigger, far more uncomfortable question about the very model used to describe how the universe grows up in the first place. Every field of science leans on a working model, a best current explanation built from decades of evidence, used to predict what should happen next. Cosmology is no exception, and its current model has faced few tests as sharp as the one these ancient galaxies are handing it right now. In cosmology, that working model has a name that sounds more like a password than a theory. Lambda, cold, dark matter, usually just shortened to the standard model of cosmology. For roughly a quarter century, it has done a remarkable job explaining the large-scale structure of the universe, the leftover glow of the Big Bang, and the slow, patient growth of galaxies over billions of years. At the heart of that model sits an invisible scaffolding called dark matter, a form of matter that does not shine, reflect, or block light the way normal matter does, detected only through its gravity. According to the model, dark matter clumped together first, in the earliest moments after the Big Bang, forming a rough, cobweb-like skeleton stretched across the young universe. Normal matter, the hydrogen and helium that eventually became stars, fell into that invisible skeleton afterward, pooling in the densest spots the way rainwater collects in the low points of a landscape. Galaxies grew inside those pools, slowly, generation by generation, following a fairly strict timetable for how quickly that growth should unfold. That timetable is precisely what these new discoveries keep testing. The model does not simply say galaxies form early. It makes a specific, checkable prediction about how much mass should exist by any given point in cosmic history, based on how quickly dark matter structures are expected to grow and how efficiently gas inside them is expected to turn into stars. Every one of the objects in this story, the impossibly massive quiescent galaxies, the too fast-growing black holes, the 10 times overweight merger, the motionless giant, tests that same prediction, and so far, each one has landed on the wrong side of the line the model draws. Scientists studying this problem generally split into two camps, and it is worth being honest about both, since neither one gets to claim victory yet. One camp suspects the observations themselves are still slightly misleading us, whether through hidden faint stars throwing off mass estimates, dust hiding a galaxy's true size, or black holes disguising their age through unusual behavior. Under this view, the standard model survives mostly intact once the measurements get sharper. The other camp suspects something in the model's underlying assumptions needs to bend, whether that means dark matter clumped faster than currently assumed, gas converted into stars more efficiently in the crowded early universe, or some other ingredient in the recipe working differently than the model currently allows. Under this view, the standard model survives, but it needs a real, structural update rather than a small correction on the margins. Neither camp has landed a knockout blow yet, and both sides keep publishing new evidence almost every month. What both camps agree on, without exception, is that this tension is not going away quietly, and it is not the first time a batch of ancient objects has forced scientists to reconsider what they thought they knew, starting with the very moment this whole modern chapter of the story earned its dramatic nickname. Every great mystery needs a name, something short and sharp enough to stick in a headline and travel far beyond the small circle of scientists who first spotted the problem. This one got its name early, within weeks of Webb's very first deep images reaching astronomers' screens, and the name has followed the topic ever since. Among the first batch of distant, ancient galaxy candidates, Webb turned up. A handful stood out immediately as far too bright and far too massive for their age, based on quick early estimates. One of the researchers involved put the situation bluntly at the time, saying it was very hard to make objects like this form so quickly in a universe only about 13,800,000,000 years old. Reporters covering the discovery reached for a phrase that captured the mood in the room better than any careful scientific term could. They started calling these objects universe breakers, and the label spread fast, jumping from research papers into headlines within days. It is worth being honest about what happened next, because science rarely moves in a straight line from shocking claim to settled fact. Follow-up observations, using more detailed instruments than the first quick images allowed, went back to check those original candidates one by one. Some held up under closer scrutiny, their extreme mass confirmed by better data. At least one did not. A follow-up study found that one of the most dramatic early candidates was likely much less impressive than first reported. Its brightness distorted by an actively feeding black hole at its center rather than by an enormous population of ordinary stars. A black hole whose glow can easily be mistaken for the combined light of billions of stars if you are not looking closely enough. That correction did not kill the story. It sharpened it. Removing one overhyped example did not erase the growing pile of separate, independently confirmed cases. The two massive quiescent galaxies, the two fast-growing black holes, the 10 times overweight merger, the motionless giant, each one checked and rechecked by different teams using different methods, arriving at the same uncomfortable conclusion from different directions. Science is supposed to work exactly this way, testing bold claims hard enough to break the weak ones, while leaving the strong ones standing taller than before. So the universe breaker's nickname survives today, not because every single early candidate turned out to be real, but because enough of them did, confirmed carefully enough by enough separate groups to earn the name honestly. It has become a kind of shorthand among astronomers for this entire category of early, oversized, over-mature objects that keep testing the limits of the standard model. A name that captures both the excitement and the genuine uncertainty still surrounding almost every object in this story. And the deeper researchers pushed into that uncertainty, hunting for still more of these early record breakers. The stranger, the objects they started finding got, drifting away from familiar, ordinary galaxies entirely and into something that barely resembled a galaxy at all, something closer to a single, impossibly bright point of light hiding a secret nobody was prepared for. Some monsters hide behind a wall, and in space, that wall is made of dust. Dust, in an astronomer's vocabulary, does not mean the fuzz collecting under a bed. It means countless tiny grains of heavier elements, cooked inside dying stars and scattered across space, drifting through galaxies in vast, dark clouds. A thick enough cloud of that dust can swallow visible light almost completely, blocking a galaxy's stars from view, the way heavy fog swallows a city skyline, even though the city is still very much there, working, glowing, and full of activity behind the haze. That blocked light does not simply vanish, it gets absorbed by the dust, which heats up in the process, then re-radiates that trapped energy back outward as infrared light, an invisible form of heat radiation rather than visible color. A galaxy could be forming stars at a furious pace, yet look almost dark and empty through an ordinary visible light telescope, its entire fireworks show smothered behind a curtain of glowing, heated dust. Catching that kind of hidden galaxy takes more than one instrument working alone. A telescope built only to see visible light would sail right past it, mistaking a roaring furnace for an empty patch of sky. Astronomers combined the sharp infrared vision of the James Webb Space Telescope with an entirely different tool, the Atacama Large Millimeter Array, a spread-out network of radio dishes built high in the Chilean desert, tuned to detect the longer wavelength glow that heated dust gives off. Together, the two instruments could do what neither one could manage by itself: spot the telltale heat signature buried behind the fog, then pin down exactly how far away and how far back in time that hidden signal was coming from. What they found sitting behind that dusty curtain was a galaxy researchers named Y1, glowing with the unmistakable signature of extremely hot, energetic dust, observed as it existed only about 600 million years after the Big Bang. Astronomers classify objects like this as warm, ultraluminous infrared galaxies, a mouthful of a label that really just means an object blazing with an enormous amount of energy, almost entirely hidden from ordinary visible light, detectable only by its heat. To a normal optical telescope, Y1 would look like almost nothing at all, a faint smudge easy to scroll past. To an infrared eye tuned to the right wavelength, it looked like a furnace. Finding a dust-shrouded galaxy at all, this early in cosmic history, was itself a small surprise. Dust normally takes time to build up, cooked slowly inside generation after generation of dying stars, before enough of it accumulates to hide an entire galaxy behind it. Finding that much dust, glowing that fiercely, in a universe barely 600 million years past its own birth, meant this particular galaxy had already lived through enough stellar death and rebirth to manufacture a genuinely serious amount of it, on a timetable that once again looked far too rushed for comfort, another young object wearing the wardrobe of something far older. And once astronomers worked out exactly how much energy Y1's dust was radiating outward, they realized the hidden fireworks show blazing behind that curtain was even more extreme than the curtain itself suggested. Every galaxy has a pace, a steady rate at which it turns raw gas into new stars, year after year, decade after decade, largely unchanged across immense stretches of cosmic time. Our own Milky Way keeps a fairly relaxed pace by galactic standards, building roughly 1 to 2 new suns worth of stars every single year. A slow, patient rhythm that has held steady for a very long stretch of cosmic time. It is the difference between a factory running one modest shift a day and a factory running around the clock with every line maxed out. One was not running a modest shift. Once astronomers calculated exactly how much energy its dust was absorbing and re-radiating outward, the numbers came back astonishing. The galaxy appeared to be forming new stars at a rate hundreds of times faster than the Milky Way manages today, and all out, no pauses, factory floor running at absolute maximum capacity, converting gas into brand new stars on a scale that dwarfs anything happening in the calmer, more settled galaxies of the modern universe. That kind of pace is called a starburst, and it does not last. A galaxy cannot sustain an all-out sprint forever. Sooner or later, it either uses up its available gas, or the sheer violence of that much star formation, including the explosive deaths of the largest, shortest-lived stars among them, blows the remaining fuel clear out of the galaxy entirely. A starburst is closer to a sudden bonfire than a controlled campfire, blazing bright and burning fast, until there is simply nothing left to fuel it. Yet a bonfire, blazing hot enough and fast enough, can build an astonishing amount of mass in a surprisingly short window of time. If a galaxy spends even a few tens of millions of years running at hundreds of times the normal star-forming pace, the total stellar mass it accumulates during that single furious episode can rival what an ordinary, patient galaxy needs hundreds of millions, even billions, of years to build the slow way. Why one may not be cheating the rules of star formation at all. It may simply be playing by a much faster, much hungrier version of the same rules. That single idea, a short, extreme burst of activity rather than one long, patient, gradual build-up, has become one of the strongest working explanations for this entire pattern of overgrown early galaxies. It does not require any exotic new physics, any hidden particle, or any secret break in the standard model. It only requires accepting that the infant universe, dense, gas-rich, and crowded with young galaxies bumping into each other, may have been capable of running its factories far harder and far faster than anything visible in the calmer sky above us tonight. Dusty starbursts, hungry mergers, motionless giants, oversized black holes, hidden populations of faint stars. Every explanation so far has stayed rooted in ordinary physics, stretched to its limit but never broken. That pattern was about to change. The moment astronomers turned Webb's gaze toward hundreds of strange, glowing red points scattered across the deepest images ever taken of the sky, objects that would push the entire mystery somewhere stranger than anyone had expected to go. A single dust-shrouded starburst like the one hiding behind Y1 is a dramatic exception. It is not, by itself, an explanation for an entire universe full of overgrown galaxies. If astronomers only found one or two extreme cases scattered across the whole sky, the mystery might stay a footnote, a curiosity for a handful of specialists. What they actually found was a widespread pattern, showing up again and again across many separate, unrelated patches of the early universe, and that pattern needed a broader idea to explain it. The leading candidate goes by the name bursty star formation, and it works a little differently than the slow, steady picture most people carry around in their heads. A galaxy does not always build stars at one smooth, unchanging rate, the way a factory might run the exact same shift every single day for years. Instead, especially in small, young, gas-rich galaxies, star formation can flicker, surging in short, intense pulses, then dying down almost to nothing, then surging again, over and over, driven by the push and pull between gravity pulling gas together and the explosive deaths of massive stars blowing that same gas back apart. Here is why that flicker matters so much for how bright and how massive a young galaxy appears to be. A galaxy caught in the middle of one of these bright pulses can blaze with far more light than its true, average stellar mass would suggest. Packed with a temporary surplus of young, hot, blazing stars formed in that single burst. Catch that same galaxy a little later, after the burst fades, and it can look far dimmer and smaller, even though its underlying population of stars has not actually shrunk. That timing problem creates a serious trap for astronomers trying to estimate galaxy masses from a single snapshot, which is essentially all a distant telescope can ever offer. Webb cannot revisit the same galaxy across millions of years to watch its brightness rise and fall. It captures one frozen moment, one single frame pulled from an extremely long, flickering movie. If that one frame happens to catch a galaxy near the peak of a bright burst, standard mass estimating methods can be fooled into reporting a bigger, more massive galaxy than the true underlying population actually contains. A study out of the University of Texas Examining a broad sample of these puzzling Webb-detected galaxies found real support for this idea. When researchers accounted carefully for the effects of both bursty star formation and, in some cases, actively feeding black holes brightening a galaxy from within, a meaningful share of the most extreme, supposedly impossible, early galaxies shrank back down toward masses that fit comfortably inside the Standard Model's rules. That correction genuinely helped. It did not close the case entirely, though. Even after accounting for every burst, every flicker, and every hidden black hole scientists could identify, a stubborn core of galaxies remained too massive, too early, and too mature to explain away. Exactly the kind of leftover, unresolved puzzle that pointed researchers toward an even stranger population of objects, waiting in Webb's deepest images, hundreds of them, glowing with a color nobody had ever catalogued before. Buried inside Webb's deepest, longest exposure images, the kind that stare at a single dark patch of sky for many hours, gathering every last drop of ancient light it can, astronomers began noticing something small, easy to overlook, and strangely repeated: tiny, faint points of light, colored a deep, distinctive red, scattered across image after image, popping up in survey after survey, far more often than anyone expected an unusual object to appear. Nobody had gone looking for them. They simply refused to stay hidden in the noise. At first, a handful of odd red points barely registers as news. Space is full of red objects, and most of them have perfectly boring explanations. Distant, ordinary galaxies naturally look redder the farther away they sit, since their light gets stretched by the expanding universe on its long journey toward us. Dust reddens things too, the same way smoke from a distant wildfire can turn a sunset a deeper shade of orange. A single red dot, on its own, would not raise many eyebrows among people who study the sky for a living. A few hundred of them, sharing an almost identical color and shape, is a very different story. What raised eyebrows was the sheer number of them, and how tightly they clustered together in both color and size. Astronomers eventually catalogued around 300 of these objects, all sharing a strikingly similar appearance: small, compact, glowing red, and sitting at almost exactly the same slice of cosmic history, dating from roughly 600 million to 1 billion, 600 million years after the Big Bang. That is a surprisingly narrow window for so many similar objects to keep turning up in, as if some particular set of conditions in the infant universe was especially good at producing them, then stopped. Astronomers gave the objects an informal, almost affectionate nickname that stuck immediately: little red dots. It is not a technical term, and it was never meant to be one. It captured exactly what these objects looked like on first glance, before anyone had the faintest idea what they actually were. A placeholder name that outlived its own temporary purpose. The moment the objects proved genuinely strange, that mystery deepened the moment scientists took a closer look at the light itself, rather than just the color and size. Ordinary galaxies tend to produce a fairly smooth, gradually changing spectrum of light across different wavelengths, following patterns astronomers have mapped out in exhaustive detail over the past century. Little red dots refused to cooperate with that expectation. Their light carried an unusual signature, distinct enough that it could not be explained away as just another, slightly redder, slightly more distant version of a normal young galaxy. Whatever these objects were, they were something entirely apart from the galaxies scientists already understood, hiding behind a color that looked ordinary enough to dismiss at first, and a light signature strange enough to demand a much closer, much more careful second look. One that would eventually reveal a spectrum shaped unlike almost anything in the astronomical record books. Every object in space carries a kind of fingerprint, written into the exact pattern of colors present in its light. Read that fingerprint carefully enough, and it can reveal an object's temperature, its speed, even what it is made of, all without ever touching it. Astronomers read that fingerprint by spreading an object's light out into a full spectrum, the same way a prism spreads sunlight into a rainbow, then studying exactly how bright or dim that light is at each individual wavelength along the way. Ordinary stars and galaxies tend to produce fairly smooth, gradually curving spectra, rising and falling in gentle, predictable slopes. Little red dots broke that pattern almost immediately. Their spectra traced out a shape astronomers began describing as a V, and it is worth picturing exactly what that means. Moving from short wavelength ultraviolet light toward the middle of the visible spectrum, these objects looked genuinely bright, packed with energy. Then, right in the middle, their brightness suddenly dropped, dipping down into a noticeable valley. Past that valley, moving further into longer wavelength optical and near-infrared light, the brightness climbed steeply back up again, often ending even brighter than where it started. Bright, then dim, then bright again, tracing a shape like the letter V turned sideways across a graph of color versus brightness. That specific shape does not show up by accident, and it does not match the light produced by an ordinary population of stars. However, you rearrange the mix of hot and cool ones, stars alone tend to produce smoother curves, without such a sharp, narrow dip carved directly through the middle. Something in these objects was actively suppressing light in that middle range, while still allowing plenty of light through on either side of the gap. Layered on top of that strange V-shape sat another clue, arguably even stranger. Many little red dots showed broad, smeared-out emission lines in their spectra, bright spikes of light at very specific wavelengths, but stretched and blurred rather than sharp and narrow. Spikes like that usually mean gas is moving extremely fast, swirling at enormous speeds close to a source of intense gravity, the classic signature astronomers associate with material spinning tightly around an active, feeding black hole. Yet these objects broke the usual black hole rulebook too. Actively feeding black holes in the modern universe almost always announce themselves through more than just visible or infrared light. They typically blast out X-rays, and often radio waves as well, both produced by the extreme physics happening in the immediate area around a black hole's feeding disk. Little red dots, for the most part, stayed nearly silent in both of those wavelengths, a black hole-like signature wrapped in an otherwise oddly quiet package, a V-shaped spectrum. Broad, blurred emission lines suggesting fast-moving gas near intense gravity. Almost no X-rays or radio waves to back that suggestion up. Every individual clue pointed somewhere different, and every attempt to force them into one clean, tidy explanation kept running into the same stubborn contradiction, the kind of contradiction that usually means the true answer is hiding somewhere nobody had thought to look yet. Sometimes, the strangest explanation turns out to be the simplest one, once you stop trying to force a mystery into a familiar shape. For little red dots, that simplest explanation pointed straight at black holes, though not the clean, bare kind astronomers were used to picturing, and not the version that first comes to mind when someone hears the words black hole at all. Start with what the broad, blurred emission lines were already whispering. That kind of smeared-out spike in a spectrum is the signature of gas swirling extremely fast, and gravity strong enough to force gas into that kind of high-speed motion, packed into a very small space, points toward one familiar culprit. A black hole, feeding on the gas and dust falling toward it, spinning that material into a bright, superheated disk before swallowing it. That part of the picture fit black holes astronomers already understood reasonably well, the same basic process powering bright, active galaxies found much closer to home. What did not fit was everything else: the missing X-rays, the missing radio waves, the strange, narrow dip carved into the middle of the spectrum. A bare, exposed black hole feeding in the open should have announced itself far more loudly across those other wavelengths, the way active black holes in the nearby universe reliably do. Something was clearly muffling the signal, filtering it, changing its shape before it ever left the object. Researchers began testing an idea that added exactly that kind of filter back into the picture. What if the black hole was not sitting exposed in open space at all, but wrapped inside a thick, dense cocoon of surrounding gas, a shroud that light from the black hole's feeding disk would have to fight its way through before escaping into the wider universe. A gas cocoon like that would not simply block light evenly across every wavelength, the way a dense cloud of ordinary dust might. Gas absorbs and re-emits light in far more selective, wavelength-specific ways, soaking up certain colors more heavily than others, and reshaping the emission lines passing through it in the process. Run the numbers on exactly how a thick cocoon of ionized gas should reshape light passing through it, and the predicted result lines up strikingly well with the actual V-shaped spectrum astronomers were seeing, dip and all. That same cocoon idea also offers a tidy explanation for the missing X-rays and radio waves. A dense enough shroud of gas can absorb high-energy X-rays almost completely before they ever escape, quietly hiding a black hole's usual loud, unmistakable announcement behind a wall. The black hole itself may have helped build out of the very material it was busy consuming. Piece by piece, the cocoon idea started explaining nearly every stubborn contradiction at once: the V-shape, the missing high-energy light, even the broad, blurred emission lines, folding them all into one single, coherent picture. What that picture implied about the size of the black holes hiding inside, though, turned out to carry its own separate surprise. Weighing a black hole is nothing like weighing an ordinary object. Nobody can place one on a scale, and nobody can walk up and measure it directly. There is no surface to touch, no edge to trace, only gravity, and the way that gravity bends the motion of whatever gas happens to be nearby. Astronomers instead rely on an indirect trick, watching how fast gas swirls around a black hole and using that speed, along with a bit of physics, to work backward toward the mass of whatever gravity is forcing that gas to move so quickly. Faster swirling gas generally means a heavier, more powerful source of gravity sitting at the center. That trick works beautifully for nearby black holes, where astronomers can measure the motion with real precision, applied to distant little red dots, using the broad, blurred emission lines as the speed indicator. That same trick produced some genuinely startling numbers, suggesting black holes far more massive than their tiny, faint host galaxies should ever have been able to grow, packing supermassive weight into objects that otherwise looked small and unremarkable. For a while, those early mass estimates fed directly into the larger universe breakers story, adding fuel to the argument that black holes in the infant cosmos must have grown impossibly fast. Then researchers pulled the gas cocoon idea back into the picture, and the math around those weight estimates started to shift underneath everyone's feet. Remember what a thick shroud of gas does to light passing through it. It reshapes the emission lines themselves, well beyond simply dimming the light evenly. And one of the ways it can reshape them is by smearing them out, broadening a spectral line beyond what the true underlying motion of the gas would produce on its own. If part of that broad, blurred emission line signature was coming from the cocoon itself, scattering and stretching the light on its way out, rather than purely from gas swirling at true black hole speeds, then earlier mass estimates built on that same broadening would have been reading a distorted signal as a clean one. A team of researchers ran the numbers on exactly this possibility, modeling how much of the observed broadening in little red dot spectra could plausibly come from a dense surrounding cocoon rather than pure gravitational motion. Their conclusion landed hard. The black holes powering these objects were likely closer to 100 times less massive than the earliest estimates had claimed, a correction roughly 2 orders of magnitude in size, moving these objects from the supermassive category down towards something far more modest. That correction did not make little red dots boring. If anything, it made them stranger and more useful. A population of black holes that only look artificially massive, hiding behind a distorting cocoon of their own making, offers scientists something rare: a chance to study relatively normal-sized black holes caught in an early, formative, still-growing stage, exactly the missing piece needed to trace how ordinary black holes eventually become the giants found anchoring galaxies today, provided the cocoon explanation itself could survive one more, even tougher round of scrutiny. Picture trying to judge the true size and shape of someone standing behind a thick pane of frosted glass. You can tell a person is there. You can catch a rough outline, a general sense of movement, maybe a blurred impression of color. What you cannot do is measure them precisely, because the glass itself is bending, scattering, and reshaping every bit of light passing through it before it ever reaches your eyes. That frustrating limit is exactly what astronomers run into when they try to read a black hole through a dense gas cocoon. Researchers studying one particularly well-observed little red dot found something that pushed the frosted glass idea from a rough analogy into something closer to direct, testable evidence. The object's spectrum carried a feature astronomers call a Balmer break, a sharp jump in brightness that happens at one specific wavelength, caused by hydrogen atoms absorbing light in a very particular way. Ordinary stars show a modest version of this jump. Our own sun shows a mild, easily recognized one. This particular object showed a Balmer break roughly 3 times steeper than the sun typically produces, an unusually sharp, dramatic version of a feature normally associated with stars, not with black holes. That detail mattered enormously, because a bare, exposed black hole feeding out in the open should not naturally produce a star-like feature at all. A black hole surrounded by a sufficiently thick, dense cocoon of gas, though, can end up mimicking exactly that kind of stellar signature, since the cocoon itself behaves a bit like the outer atmosphere of an enormous, extended star, reshaping the escaping light in a similar way. Researchers gave objects showing this pattern a fittingly strange nickname: black hole stars. Not stars in the traditional sense, powered by nuclear fusion in a core, but black holes dressed in a costume borrowed from stellar physics, wrapped in gas thick enough to reshape their light into something that looks, at first glance, remarkably like the spectrum of an actual star. That discovery did more than support the general cocoon idea. It offered something close to a smoking gun, a specific, testable feature predicted by the cocoon model, and then genuinely found sitting inside the data, rather than simply proposed to explain away an inconvenient contradiction after the fact. Science tends to trust explanations far more once they start making successful predictions, rather than just patching up old problems. None of this fully closed the case, and researchers working on little red dots are careful to say so openly. The cocoon model explains an impressive amount, yet a population this large, this strange, and this newly discovered was never likely to yield to a single, tidy explanation on the first attempt, or even the second. A second major theory was already gathering support, one that focused less on hiding a black hole's true size, and more on an entirely different question: just how fast these black holes might actually be feeding. Remember the speed limit built into ordinary black hole feeding, the Eddington limit, the natural brake pedal that keeps a black hole from swallowing gas faster than the resulting glow can push new material away. That limit is not a suggestion. It is close to a hard boundary, baked into the physics of how radiation pressure and gravity fight each other near a feeding black hole. Cross it too far, for too long, and the whole feeding process should choke itself off. A separate team of researchers, studying little red dots from a different angle than the gas cocoon idea, built a theoretical model that pushes directly against that supposedly hard boundary. Their proposal treats little red dots not as black holes wearing a disguise, but as black holes caught mid-tantrum, feeding in rare, violent, short-lived bursts that genuinely exceed the normal Eddington limit for brief stretches of time, gulping down gas faster than the standard rulebook says should be physically sustainable. That sounds like it should break physics outright, and it is worth being precise about why it does not. Even the strict version of the Eddington limit assumes a fairly simple, tidy setup, gas falling in smoothly and evenly from every direction at once. Real gas clouds are messier than that, clumpy, uneven, sometimes falling in faster from one direction than the outward pushing light can hold back. Under the right chaotic conditions, a black hole can briefly gulp down gas at rates that spike well past the steady-state limit in short, violent bursts, rather than one long, sustained binge before settling back down to a calmer, slower pace. Researchers building this model call it the bursty branch of black hole growth, and it carries a genuinely striking prediction along with it. If little red dots represent black holes caught specifically during these rare, intense feeding bursts, then the ones bright enough for Webb to actually detect and catalogue should only be the tip of a much larger iceberg. A far larger population of similar black holes, caught in the same violent growth phase, but simply less luminous at this particular moment, should be sitting just below the detection limit of current telescopes, waiting quietly for a sharper instrument to finally catch them. That prediction sets up a genuinely useful test, the kind science depends on to separate a good idea from a merely clever one. If future, more sensitive observations turn up exactly this kind of hidden, larger population lurking just out of reach, the bursty feeding model gains serious ground. If that predicted population never materializes, the idea will need serious revision or abandonment altogether. Two competing pictures, then, both still very much alive in the scientific conversation. One says these objects are ordinary black holes wearing a thick, distorting disguise. The other says they are ordinary black holes caught briefly breaking their own supposed speed limit. Both explanations point toward the same underlying object, a black hole in the earliest, roughest stage of its life, and both raise the exact same unsettling question about what that growing black hole might actually look like up close, if anyone could ever get close enough to see it. Close your eyes and try to picture a black hole feeding at the ragged edge of what physics allows, 13 billion light-years away, in a universe still barely out of its infancy. There is no clean, simple image for it, no single postcard snapshot that captures the whole scene. Because what is actually happening involves violence on a scale that resists easy comparison, stitched together, instead, from a handful of ordinary, everyday images, layered one on top of another. Start with the gas itself, not falling gently and evenly, the way water spirals calmly down a drain, but tumbling in unevenly, clumped and uneven, arriving in surges rather than a smooth, steady stream. Picture a crowd trying to squeeze through a single doorway during a sudden, unexpected downpour. No orderly line, just a chaotic crush of people, all trying to get through the same narrow gap at once, some getting through in a rush, others piling up and pushing from behind. Now add heat and light to that crowded doorway. As gas crushes inward toward the black hole, friction and gravity heat it to extreme temperatures, tens of thousands of degrees or more, blazing with radiation across a huge range of wavelengths all at once. During an ordinary, steady feeding phase, that light pushes back hard enough to keep the crowd moving through the doorway at a controlled, manageable pace. During one of these theorized bursty episodes, the crowd outpaces the light's ability to hold it back, gas shoving its way in faster than the glow can slow it down, at least for a while. Wrap all of that inside a thick, smothering cocoon of surrounding gas and dust. The shroud researchers now suspect surrounds many of these objects, and the picture gets murkier still. Light escaping from that violent, overcrowded feeding process has to fight its way out through the cocoon first, getting absorbed, re-emitted, and reshaped along the way, arriving at our telescopes not as a clean, sharp signal, but as the blurred, V-shaped, oddly muffled spectrum astronomers have been puzzling over. From 13 billion light-years away, none of that inner chaos is directly visible. What actually reaches Webb's mirror is a single, tiny point of red light, faint and compact, giving almost no visual hint of the violence folded up inside it. The drama is entirely encoded in the spectrum, not the image, hidden in the exact pattern of brightness and dimness spread across different wavelengths. waiting for careful analysis to translate that pattern back into a scene of crushing gravity, blinding heat, and gas pushed to its absolute physical limit. It is a genuinely strange kind of astronomy, reconstructing an entire violent, active scene from nothing more than a single point of light and the careful mathematics hiding inside its colors. And that same forensic approach, reading violence out of a quiet-looking dot, would soon lead researchers toward an even stranger possible identity for these objects, one that had nothing to do with a black hole feeding at all. Every explanation so far has kept little red dots firmly in the category of black holes, disguised in different ways but fundamentally the same underlying object. One team of researchers, working through the same puzzling spectra, started asking a genuinely different question, one that pulled the whole conversation in an unexpected direction. What if some of these objects were not black holes at all? Not yet, but something caught in the final, brilliant moments just before becoming one. The idea centers on a genuinely strange class of object called a supermassive star, a theoretical stage of stellar life so extreme that almost nothing in the modern universe produces one. Ordinary stars, even the largest ones burning today, top out at somewhere around a few hundred times the mass of our Sun before their own internal pressures make anything larger too unstable to hold together for long. Supermassive stars push far past that ordinary ceiling, potentially reaching masses close to 1 million times heavier than our Sun, an object so large and so unstable that it can only exist briefly and only under the dense, gas-rich, chaotic conditions found in the very early universe. An object that extreme does not behave like a normal star on the inside. Its core burns through nuclear fuel at an almost unimaginable rate, generating enormous amounts of energy that has to fight its way out through an outer envelope so vast and so puffed up that it barely resembles a conventional stellar surface at all. That bloated, extended outer layer lowers the star's surface temperature dramatically, even while its core rages at extraordinary heat, giving the whole object a distinctly red, cooler outer glow, despite the furnace burning away underneath. Researchers modeling the expected light from a supermassive star found something that stopped them in their tracks. The predicted spectrum lined up closely with the actual, observed spectra of at least some little red dots, matching the general red color and also specific, detailed features in the light, the kind of match that is much harder to produce by accident than a loose, general resemblance. That match matters because of what comes next in a supermassive star's short, violent life. An object that massive and that unstable cannot burn steadily for billions of years the way an ordinary star does. It burns fast, and it ends fast, collapsing directly under its own crushing weight once its fuel runs out, most likely straight into a black hole, skipping the more gradual, drawn-out stages that smaller, ordinary stars pass through on their way toward that same eventual fate. If that interpretation holds up, at least some little red dots may not be feeding black holes wrapped in a disguise at all, but something even rarer, massive dying stars, caught in the brief, brilliant window right before their own collapse, offering scientists an almost unprecedented direct look at the exact moment a black hole seed is born, rather than a black hole already grown and already feeding. Every black hole needs a starting point, a first seed of collapsed matter that later growth can build upon. Nothing in the universe grows from nothing, and black holes are no exception to that basic rule. For decades, the standard starting point in most models was fairly modest: a single massive star, dying in a supernova, collapsing down into a black hole weighing somewhere between a few and a few dozen times the mass of our Sun. Small seeds, growing slowly over enormous stretches of time, gradually feeding their way up toward the supermassive giants found anchoring galaxies today. That standard starting point runs into exactly the same speed problem that has followed this story from its very first chapter. Small seeds, growing under the normal Eddington feeding limit, simply do not have enough cosmic time to reach the sizes astronomers keep finding inside the early universe. especially once actual observations, rather than theoretical assumptions, are taken into account. A supermassive star collapsing directly into a black hole at the end of its short, violent life offers a genuinely different starting point and a considerably more generous one. Instead of beginning with a seed weighing a handful of solar masses, this kind of collapse could hand a newborn black hole an initial mass measured in the tens of thousands or even hundreds of thousands of solar masses, essentially skipping several of the slow, patient growth stages a smaller seed would otherwise need to survive. Researchers behind this idea describe it in almost literal terms, framing these objects as a direct window into a black hole's birth, rather than indirect evidence pieced together after the fact. One scientist working on the topic put it plainly, saying the team was not simply guessing that heavy black hole seeds must have existed somewhere in the early universe. They were, in their own words, watching some of them be born, capturing the actual transitional moment rather than reconstructing it secondhand from an already grown, already feeding black hole much later in its life. That distinction carries real scientific weight. Most evidence for black hole growth comes from studying objects long after their formative, chaotic beginning, working backward through indirect clues to guess at a birth nobody actually witnessed. A confirmed population of collapsing supermassive stars would instead hand astronomers something close to a direct, observable birth certificate, a documented transition from star to black hole, caught in the act rather than inferred after the fact. None of this rules out the black hole explanations covered earlier. Both ideas may well turn out to be true at once, describing genuinely different objects that happen to share a similarly strange, red appearance in Webb's images. Some little red dots may be feeding black holes wrapped in a distorting cocoon. Others may be dying supermassive stars, delivering an oversized seed directly into a black hole's first moments of existence. Either path, once it finishes, arrives at the exact same kind of question: just how large can a single seed be allowed to start out, before growth even properly begins? There is an even more extreme idea circulating alongside the collapsing star scenario, one that skips stars out of the picture almost entirely. Instead of a black hole forming from the wreckage of a star that lived and died first, this idea proposes a black hole assembling directly from a massive cloud of raw gas, collapsing straight down under its own gravity without ever passing through a normal stellar life cycle at all. Scientists call it direct collapse. Under most conditions, a massive cloud of gas does not behave that simply. As gas gathers and compresses under gravity, it heats up, and that extra heat normally pushes back hard enough to slow the collapse, breaking the cloud apart into smaller, separate clumps along the way, each clump eventually settling down into an individual star rather than one single enormous mass. That fragmentation process is exactly how ordinary star formation usually works, and it is normally quite effective at preventing gas from simply piling up into one giant, unbroken blob. Direct collapse requires something to disable that usual fragmentation process, at least temporarily, allowing an enormous reservoir of gas to keep collapsing as one single unit instead of breaking apart into countless smaller stars. Researchers have proposed a few specific conditions that could pull this off in the early universe, including intense radiation from a nearby, already active galaxy, strong enough to strip away the particular molecules gas clouds normally rely on to cool down efficiently and fragment. Without that cooling, a gas cloud stays hot, stays whole, and keeps collapsing as a single overwhelming mass, right up until it crosses the threshold into forming a black hole directly, no intermediate star required. A black hole born this way could start out enormous from its very first moment of existence, potentially reaching tens of thousands or even hundreds of thousands of solar masses instantly, rather than earning that mass gradually through millions of years of careful, limited feeding. It is the difference between a company built up slowly, one careful hire at a time, and a company that opens its doors on day one, already fully staffed, funded, and running at scale. If direct collapse black holes really do form this way, somewhere in the early universe, they would solve the growth speed problem in the most direct manner imaginable, not by bending the feeding rules, and not by disguising a smaller black hole behind a distorting cocoon, but by starting the race from a wildly different position than anyone assumed possible. Researchers studying little red dots have begun exploring whether some of these objects might represent exactly this kind of birth, the visible aftermath of a gas cloud that skipped the star-forming stage entirely and collapsed straight down into a black hole seed, heavy enough to make every later growth problem in this story simply disappear. Whichever origin story turns out to be correct, collapsing stars, direct collapsing gas, or some combination of both working in different places, the implications reach the exact same conclusion. The early universe appears to have been capable of manufacturing seriously oversized black hole seeds through more than one separate pathway, a discovery that would have sounded like pure speculation only a handful of years ago, and now sits at the center of one of astronomy's most actively contested debates. Every idea covered so far, the gas cocoons, the bursty feeding, the collapsing supermassive stars, the direct collapse seeds, tries to explain how a single black hole could grow abnormally fast in the early universe. A discovery announced in the summer of 2026 raised a very different kind of question. What happens when a single early galaxy is not hosting one oversized black hole, but three of them, active, feeding, and crowded together inside the same small patch of space? An international team of astronomers, using Webb's ability to separate overlapping sources of light with remarkable precision, examined a distant galaxy sitting more than 12 billion light-years away, observed as it existed roughly 1,200 million years after the Big Bang. Buried inside that single galaxy, they identified not one, but three separate, actively feeding supermassive black holes, each one confirmed through its own distinct, broad emission line signature, the same telltale marker astronomers use to identify actively growing black holes elsewhere in this story. No galaxy had ever been confirmed to host three separate active black holes at once before. Two of the three sat remarkably close together near the galaxy's center, separated by a distance that would fit comfortably inside a single, modest-sized galaxy neighborhood, while a third sat farther out, closer to the galaxy's outer edge, likely a leftover signature of an earlier collision that brought an entire separate galaxy, black hole included, crashing into the system. The lead researcher on the discovery described it as the first clear evidence of three active black holes sharing a single galaxy this early in cosmic history, a genuinely rare configuration that offers a direct, physical link between two separate ideas explored earlier in this story. Galaxy mergers, the same violent collisions responsible for building oversized stellar mass quickly, appear equally capable of delivering multiple black holes into one shared home, setting up future collisions between the black holes themselves. That detail carries weight far beyond a simple curiosity. The two central black holes in this system sit on a slow, inevitable collision course of their own, expected to merge together within the next several 100 million years, a preview of the kind of black hole merger events that future gravitational wave observatories are specifically being built to detect and study. Watching that kind of merger unfold, whether through gravitational waves or future telescope observations, would offer scientists a genuinely direct look at exactly how supermassive black holes combine and grow. Findings like this reinforce a pattern that keeps resurfacing throughout this entire story. Mergers are not a rare, occasional shortcut scattered here and there across the early universe. They increasingly look like one of the primary engines driving nearly everything strange found in this era, stitching together oversized stellar mass, oversized black holes, and now, apparently, entire crowded families of black holes sharing a single early galactic home. Every measurement in this story carries a hidden assumption worth pausing on, one easy to overlook in the rush of dramatic new discoveries. Even the most careful astronomer can only study what the telescope actually manages to catch, and that simple limit shapes the whole story more than most headlines let on. Telescopes do not survey the universe evenly. They tend to notice bright things far more easily than faint things. The same way a person scanning a dark parking lot at night will spot the one car with its headlights on, long before noticing the dozens of parked cars sitting quietly in the shadows nearby. That simple, unavoidable bias toward brightness turns out to matter enormously when scientists try to judge just how unusual the earliest supermassive black holes really are. Here is the specific worry. When astronomers compare a black hole's mass to the total mass of stars in its host galaxy, nearby galaxies tend to follow a fairly consistent ratio, a rough rule of thumb built from decades of careful, close-up study. Early reports on distant black holes suggested that ratio was being broken dramatically, with black holes appearing far heavier relative to their host galaxies than the nearby rule would predict, feeding the broader universe breakers narrative running through much of this story. A team of researchers decided to test whether that apparent break might partly be an illusion created by which galaxies telescopes are even capable of detecting in the first place. In the extremely distant, faint early universe, only the very brightest galaxies clear the detection threshold at all. If a black hole happens to be feeding especially brightly at the exact moment it gets observed, that brightness makes the entire galaxy easier to spot and study. Even if the black hole's true, typical mass relative to its galaxy is not actually unusual. Running detailed statistical models on a large sample, roughly 2,000 early universe galaxies, pulled from Webb's stacked spectral data, researchers found meaningful support for exactly this selection effect. Once they accounted carefully for which objects telescopes were realistically able to detect in the first place, a substantial share of the apparently overmassive early black holes moved back toward the same ratio seen in galaxies much closer to home, no longer standing out as dramatically abnormal once the detection bias itself was properly subtracted out of the picture. That finding does not erase every strange object covered earlier in this story. Genuine outliers still remain in the data, black holes and galaxies that stay stubbornly oversized even after every known selection effect gets carefully accounted for. What this research does accomplish is narrowing the mystery, separating a smaller, harder core of genuinely unexplained objects from a larger surrounding population that may simply reflect the ordinary, unavoidable limits of what a distant telescope can and cannot see. Science tends to advance exactly this way, not through one single dramatic discovery settling everything at once, but through a slow, careful back and forth. One team proposing something extraordinary, another team testing whether ordinary explanations might account for part of it, narrowing the gap a little further with each careful round of scrutiny, leaving behind a smaller, tougher, more trustworthy mystery each time. Step back from any single object in this story, and a longer list starts forming almost on its own. Quiescent galaxies carrying more mass than their light first suggested. A merger caught building a monster 10 times faster than its neighbors. A giant galaxy moving like a battle-scarred veteran while barely out of its cosmic infancy. A dust-wrapped furnace churning out stars hundreds of times faster than our own galaxy manages today. Black holes that grew too fast, or only appear to have grown too fast, wrapped in cocoons, caught mid-burst, or born already enormous from a collapsing star or a collapsing cloud. 3 black holes crowded into one impossibly young galactic home. Every model, built to explain how galaxies and black holes form, now has homework to do. Whether or not any single explanation offered so far turns out to be the final, correct one. That homework breaks down into a short list of genuinely hard, currently unresolved questions, each one a direct consequence of everything covered across this story so far. The models need to explain how gas in the infant universe could collapse into stars and into black holes, on a timetable far tighter than earlier versions of the standard model comfortably allowed, whether through faster gas cooling, denser initial conditions, or some other ingredient nobody has fully identified yet. They need to explain why galactic mergers appear to happen so early and so often in this era, delivering oversized mass and multiple black holes into single systems well before the universe had. By older estimates, any business hosting that kind of crowded chaos, they need to account for a star-forming recipe that may lean more heavily towards small, faint stars than the modern, nearby universe does. A shift with consequences reaching all the way from galaxy mass estimates to the potential number of small, rocky planets scattered through the early cosmos. They also need to explain the black holes themselves, how heavy a starting seed the universe was capable of producing in the first place, on top of how fast they can feed, whether from a single collapsing supermassive star, a directly collapsing cloud of primordial gas, or some combination working differently in different environments. And they need to do all of this while accounting honestly for observational bias, separating genuine physical extremes from objects that merely look extreme because of which galaxies happen to be bright enough for a distant telescope to catch. That is an enormous amount of homework for one working model to absorb all at once, and it is worth being honest that no single updated version of the standard model has yet managed to check every box cleanly. Some of these threads may resolve into the same underlying explanation once researchers connect them properly. Others may turn out to describe genuinely separate processes, each contributing its own piece to an early universe that behaved far more energetically than anyone expected. Either way, the growing pile of homework points toward the same underlying conclusion. Whatever comes out the other side of this era of discovery, the tidy, patient early universe imagined for decades has already been left behind. Every galaxy in this story sits at a distance, and every distance carries an uncertainty attached to it, even though headlines rarely mention that part. Pinning down exactly how far away, and therefore exactly how far back in time, a single ancient galaxy actually sits, turns out to be one of the hardest, most technically demanding parts of this entire field. The quiet, unglamorous work standing behind every dramatic headline in this story. The details matter enormously for judging just how strange any single object really is. Astronomers use two broad methods to estimate a galaxy's distance, and they do not carry equal weight. The first, called photometric redshift, works quickly and cheaply, estimating distance from a galaxy's general color and brightness across a handful of broad filters, a bit like guessing someone's age from a quick glance rather than checking their birth certificate. It works well enough for large surveys covering thousands of galaxies at once, but it carries real uncertainty, and it can occasionally be fooled by dust, unusual chemistry, or an active black hole skewing a galaxy's color in a misleading direction. The second method, called spectroscopic redshift, works far more precisely, splitting a galaxy's light into a detailed rainbow and measuring the exact wavelength shift of specific, well-understood features within it, the astronomical equivalent of checking that birth certificate directly rather than guessing from appearances. It takes far more telescope time to gather, and it is simply not practical to run on every single distant candidate astronomers stumble across. That gap between quick estimates and precise confirmation matters enormously for a story built almost entirely on record-breaking ages and record-breaking masses. Several of the most dramatic early claims in this exact field, including some of the original universe breaker candidates, first appeared using the faster, less certain photometric method, generating exciting headlines well before slower, more careful, spectroscopic follow-up could confirm or challenge them. Some held up beautifully under that follow-up scrutiny, at least one did not, revealing itself as a much less extreme object once better data arrived, its apparent brightness distorted by an active black hole rather than genuine stellar mass. That pattern means every single record mentioned throughout this story carries an invisible asterisk, worth remembering honestly rather than glossing over for the sake of a cleaner narrative. Some objects, like the confirmed merger, the confirmed non-rotating giant, and the triple black hole galaxy, rest on solid, carefully checked spectroscopic ground. Others still await that same level of confirmation, sitting in a genuinely uncertain middle zone between exciting candidate and fully verified discovery. None of that uncertainty means the broader mystery is somehow fake or overstated. Enough objects have cleared the highest bar of confirmation to keep the puzzle firmly, legitimately open. It does mean that the exact edges of this story, the single oldest galaxy, the single heaviest early black hole, the single most extreme outlier on any given list, remain genuinely moving targets, likely to shift, sharpen, or occasionally soften as better instruments and more patient follow-up observations continue rolling in. 32 chapters ago, this journey opened with a simple, almost childish image. A newborn stepping out of the delivery room, already running a company. Everything that followed was an attempt to explain how something that's strange could possibly be true, not once, not in a single isolated case, but scattered across dozens of separate, independently confirmed objects, found by different teams, using different instruments, in different corners of the sky, all telling some version of the same impossible story. A galaxy carrying 100 billion suns worth of stars before its first billion years were even finished. 9 retired galaxies hiding even more mass than anyone first measured, their true weight buried inside a population of small, faint stars. Nobody had a clean way to count until very recently. A merger caught mid-collision, building a monster 10 times heavier than anything nearby, in an event that likely was not rare at all, given how crowded and violent the infant universe appears to have been. A giant galaxy moving like it had already lived a long, eventful life, standing as a direct challenge to how astronomers judge a galaxy's age. A furnace of a galaxy, hidden behind a wall of its own dust, burning through star formation at a pace that would put any modern galaxy to shame. Then came the black holes, growing faster than the physics of ordinary feeding should allow, followed by hundreds of strange red points scattered through Webb's deepest images, objects that turned out to be even harder to pin down than anything before them. Cocoons of gas disguising true masses, bursts of feeding pushing past supposed speed limits, dying supermassive stars caught mid-collapse, handing over an oversized seed to the very first moments of a black hole's existence. Clouds of primordial gas skipping the star-forming stage entirely. 3 black holes, somehow, crowded into a single early galactic home. Running underneath every single one of these individual stories sits the same unresolved tension. Either the standard model of how the universe grows needs real, structural revision, built to account for a faster, hungrier, more violent infant cosmos than anyone designed it to describe, or an entire generation of ancient, extreme objects has been quietly fooling careful observers through selection bias, hidden mass, and light bent and blurred by billions of years of travel. Both camps have real evidence behind them. Neither has landed a final, undisputed answer. That is not a disappointing place to end a story. It is closer to the most honest place any real scientific mystery can end, with a puzzle sharp enough to keep hundreds of researchers testing, arguing, and observing long after this particular script goes quiet. Somewhere out past the edge of what any telescope has managed to see so far, the true first galaxies are still sitting there, patiently waiting in the dark, exactly as old as they have always been, for the day some sharper instrument finally reads their light correctly and settles, once and for all, just how impossibly early the universe learned to grow up.